Hello, my name is Mingqiu and I'm from Google Deepmind. Today I'm presenting our paper, SLM, which is a joint speech and language model. So first, I'm going to give a quick highlight of our work. SLM is a model which joined the two pre-trained foundational models, a frozen acoustic model and a frozen large language model using a speech-to-text adapter. This model enables multitask, multilingual, and dual modalities. Basically, we have one adapter for different tasks, ranging from speech recognition, translation, dialogue, and more. Our model supports 75 plus languages, support speech plus text input. We also demonstrate in later slides that we have strong recognition and translation performance. This model is robust and generalizable beyond the given SINT prompts, but also is able to attend to zero-shot instruction following. We show that our model is light-weighted. We only use 1% of the trainable parameters of the frozen foundational models, and it's easy to plug in, which can adapt to any pre-trained speech model and any pre-trained language models. So first, let's take a look at some demos of what is this multitasking model. Say we have a frozen speech encoder here, and we have a pre-trained large language model here. SLM basically just trained adapter layers between these two foundational models, and then enables a large language model also be able to handle the speech content. So for example, if the speech content is, I would like to book a table for 2 people at 6 p.m. today, if the model is given the instructions such as recognize this speech, the prediction to our model would be, I would like to book a table as what is in the speech content. While if you instruct the model to be what time it is, the model's prediction would be 6 p.m., which is the time for the booking. If you ask how many people, the model is able to follow the instructions saying there are 2 people involved, or you can also do the translation task to translate to any languages. I would like to book a table for 7 people at 6:30 p.m. today. Thank you. So here's a living demo of what's going on using our model. Basically, the audio content is what is in this speech, while the prompt is the text instruction given to the model, while the prediction is, for example, in this case, we instruct the model to recognize the speech. The prediction is the transcript of the speech. While if you are giving the model different instructions, such as now, how many people, and then the model is able to predict. Hello, I would like to book a table for 7 people at 6:30 p.m. today. Thank you. So in this case, there are 7 people are mentioned. So follow this instruction, the model answers 7. Hello, I would like to book a table at 6:30 p.m. for 7 people. Thank you. And now answer is 6:30 p.m. because the time mentioned is 6:30 and the instruction is what is the time. And there's another example. I would like to book a table for 7 people at 6:30. Website demo is made by my colleague Han Wei. So here, first, if we do the normal speech recognition task, the prediction is, say, my colleague Han Wei. Actually, it's like a wrong prediction for the name of my colleague. While the model is able to take like the context information, say if we know that my colleague is called Han Wei, and then the model is able to predict correctly to this. This website demo is made by my colleague Han Wei. So see here, like if I know that my colleague, including those people, well, Han Wei's spelling is this like this, and then after the model see this prompt, it's able to bias into the correct name of my colleague. And this example is, hello, I started feeling unwell since last night. I had a headache and I feel very tired, so I took a pill of ibuprofen and went to bed early. So this speech describes some medical conditions of the speaker, and if you just do recognition, it gives you the transcription prediction. Hello, I started feeling unwell since last night, and I had a headache, and I feel very very unwell. So I took a pill of ibuprofen and went to bed early. Now, if you instruct the model with what symptoms is mentioned, instead of predicting the transcript, the model is able to tell, oh, headache which is a symptom, is mentioned in this speech. Or you can also ask what medication is mentioned as following in this instruction. Hello, I started feeling unwell since last night. I had a headache and I feel very tired. So I took a pill of ibuprofen and I went to bed early. And now the model is able to mention ibuprofen here. And next is the multilingual translation task. Hello, I started feeling il fait beau aujourd'hui. On peut faire quoi? So the model is able to recognize French, and also if you just ask the model to translate, it can also translate from French to English. Il fait beau aujourd'hui. On peut faire quoi? Je voudrais réserver une table pour 2 personnes à 17h, s'il vous plaît. So one thing you can notice here is we allow the model to choose a language, a source language, but this is optional. If the source language is given, the model is able to predict more accurately. But without the source language, the model is also able to recognize. Okay, now since we've already seen some demos, and next question is how this model works and how do we train that? So basically, first we choose the pre-trained acoustic and language models. For example, in our case, we choose the speech encoder from the Google USM and then the text model from the Google T5 family. And then we run the speech encoder to obtain the speech encoding. And in this case, we have the speech in, and then we get to the speech representation after the encoder, and we adapt them as a third step to the large language models. First step is we reduce the length of the speech encoding. This allows the model to be able to handle longer lengths of the speech input. But also if we don't do the speech reduction, it also works. And second, we feed the speech encoding to the adapter, the trainable adapter here. And after the model, the adapter model takes the speech encoding and it produces the representation, the speech representation. We call that speech embedding, and we concat the text embedding together with the speech embedding together. So now the text it can be different speech text instructions. In this case, the text input is how to reply to this customer, while the speech input is I would like to book a train to blah, blah, blah. Okay, so after we concat these two embeddings together, the whole thing is fed into the language model. And then the frozen language model is taken this, the concatenated embedding, and then to train with the regular language model objective on the target. So basically, the role of the adapter here is to force the speech encoding into the text embedding space so that the speech embedding can be also processed by the frozen language models. So in this case, you can say both the pre-trained speech encoder and text encoder are frozen. Optionally, we can also do further fine-tuning on either of the foundation model weights, or we can also apply the LoRa or residual other adapter to the pre-trained models so that it can get a better fine-tuning performance. So here are some results we show. First, we have run the speech recognition and translation. In this table 1, we have the speech recognition result in a wide range of different tasks from speech stew, vox populi, and FLIR. And in the table 2, we show the speech translation result on the CoVost2 test set. And we achieve pretty good performance compared to USM. And then here for the translation compared to other benchmarks. We also show the Slim FT, which is the fine-tuning the decoder part of the LLM. You can see that after fine-tuning, the model performance even first boost so that our Slim fine-tune achieved a similar performance as the state-of-the-art translation audio pump. So next is not only our model shows the traditional conventional ASR or translation, but we can also instruct the model with the zero-shot prompt, which the model was not seen during its training time. So here's an example, the contextual ASR. Say if we want to recognize a voice search, and the voice search is conditioned on different users' context list. So for example, this user has this like a contact names. And if the model is able to condition on that, generally the model can do a better job in the contextual speech recognition. So for the regular ASR case, we simply prompt the model with recognize this speech. While if we do the contextual biasing case, we prompt the model with recognize this speech with such mention, and we retrieve top K entities from the personalization list. The speech retriever we are mentioned in another paper that we are going to link later. So in this case, you can see our model achieves pretty good performance. Let me see if I can show more of this table. Yeah, here. So the model shows very good performance after we prompt with the retrieved entities. ASR column here refers to the regular ASR, while CASR means the contextual ASR with the biasing. Without even fine-tuning a little bit of the model, the Slim shows the word rate goes from 14% to 8%, and then for this case, 32% to 17%. If we further do the fine-tuning of our model, and you can see that for this case, and we achieve the state-of-art in this ACS biasing dataset. And besides of the contextual ASR, our model is able to do more open-ended generation tasks. So for example, if we have the audio content here, and then we show the model is able to react in different ways given different instructions in the previous demo, or it can also do the biasing. And here are some natural question tasks. So we use the TTS to synthesize the natural question dataset and then ask the model to do the answering. For example, if the audio is given the formula of the following substance, carbonic acid, and then the model is able to answer this. And while the model can also answer the phase where the cell does not divide, so those different questions. But we also saw there are some mistakes made by the model. So for example, let me move this here. So you can see that the year that the death penalty reinstated in Oregon is responded wrong. In this case, how many wars held in between India and Pakistan was also answered wrong. This is mostly because the model tends to hallucinate. Although the model learns to follow follow the instruction to answer the question, but the model is not able to answer the question correctly, mostly because of the quality we used to adapt to, in this case, MT0MT, and it performs badly in this QA task. If we change the LLM which it adapts to a better, higher quality LLM, generally this question can be resolved. So now we have some findings of the model. First one, in our paper, we show the T5 family, but our model also works well for the decoder-only LLM, for example, PaLM, which is not shown in this paper, but we have some internal result. And the second one is the adapter. So the adapter was pretty thin since we talked about that earlier. We observed that if we improve the if we increase the adapter layer from 1 layer to 2 layers, we indeed saw improvement. However, this improvement saturates after 2 layers. So this implies that the representation gap between the pre-trained speech model and the text model might be narrower than expected, and it can be simply bridged by a shallow adaptation. For the LLM, as in the failure cases in the NQ dataset, the adaptation layer itself only provides the transformation from the speech modality to text modality, but hardly stores the word knowledge as in the LLM itself, while instruction following or reasoning ability is determined by LLM. So in order to get the optimal instruction following ability, LLM quality is really important. We show that we only train adapter versus fine-tuning LLM as well. So optional further fine-tuning with LLM on frozen definitely boosts the performance, as we see in the ASR and the AST cases. Also, we can use the adapters such as LoRa and the residue to behave similar as the fine-tuning on LLM without unfreezing the weight of the LLM itself. And this can be used to tailor to a specific downstream task and then to achieve the optimal quality. People may also ask, if we can just recognize the speech and then we feed the transcript to the downstream LLM, and the cascaded system can also be pretty powerful. So we did a comparison between the cascaded and end-to-end system, and we saw that in the translation task, indeed, we see the significant performance drop when directly feeding the ASR transcript to LLM. For example, in CoVoS 2, French to English shows the blue score goes down from 38 to 31, and when changing from SLM to the cascaded approach. Partially, the reason is because the LLM itself, which is the T5, is not very robust to the ASR transcript. So if we have the speech transcript robust LLM, the model performance should be better for the cascaded system, while the end-to-end also have some advantage, and end-to-end can preserve more information in the speech. So for example, if we go beyond the speech, we have more emotion and we have more background speech and then a background noise. The end-to-end model is better to handle that. Or if we can ask the model to correct the pronunciations and then to help the language learning, and the end-to-end system also has more advantage. But here, truly, if the LLM itself is robust to the speech recognition transcript, the cascaded can also be very powerful. But in our model, we just show an option that the end-to-end can also does a good job in many zero-shot prompting tasks. So that is our presentation. Thank you for listening. And this is my email address. Feel free to let me know if you have any question. Thank you.